In this session, we're going to be looking at side channel attacks. First, we're going to talk about them in a broad sense, and then we're going to look at some specific scenarios that can occur in the browser. So what is a side channel attack? In general, it's a type of attack that leverages information that is leaked as a byproduct of a system's operation. I thought this was the best way to classify and to define side channel attacks. Typically, the information that you're able to obtain from these was not intended. It is a side effect of some way in which that system works, and by being able to obtain information that leaks through that channel, you can infer things about the primary information and state that the application or the system is intending not to reveal. And we're going to open here with a non-web application related example, but just a kind of fun example. Still technology, of course, because there are many examples like this of unintuitive side channel leaks that have occurred in the real world. You can find all kinds of interesting ways in which information technology broadly has failed to consider the ways in which information can leak through different mechanisms. So in this example on screen, this is a situation where a power LED fluctuates very slightly on a device in relation to activities of that device. And there have actually been a few different cases of this type of side channel leak through some like power LED that you can observe with a camera. And in the example you see here, we're looking at a device from quite a distance with a camera. And of course, it is a controlled environment, but nevertheless, there is a proof of concept that permits the observer with the camera to determine cryptographic key material from just observing the light. The light is not the primary channel of the device we're looking at. The light is just a little indicator that was built that surely the original designers did not think in any way would leak information. It is just a light that goes on and off, but it goes on and off with sufficient connection to underlying processes within the otherwise closed system that allows an observer to extract information from that. And there are so many of these types of attacks that are still being discovered. I'm sure there are new interesting types of side channel leaks that are yet to be discovered that we will learn about and be worried about when those are released. And there are, of course, a number of different types of side channel attacks. There are different ways in which systems can leak information. The first one that we're going to look at is timing based. So situations where there is something that happens and you're able to look at how long that takes or the difference in time between two different operations, and that allows you to determine ultimately what was going, make some inference about what occurred based on that timing. So these timing differences can generally result from differences in computational paths. You can, I'm sure, imagine situations that require large amounts of computation compared to little amounts of computation. Network latency, of course, can introduce time differences. It can take you, let's say you're observing traffic, but you can't see the ultimate destination IP addresses. Well, if a target server is on the other side of the world compared to on the local network, probably the request that goes to the other side of the world will take longer to receive the response. So you can infer certain things about the nature of communication sometimes from the timing. Memory access patterns, especially when dealing with caches, can also leak information through timing, right? If a system has cached something, it's not going to take the same amount of time to retrieve that information as opposed to something that is not cached, that either needs to be looked up or has to initiate a network connection out to retrieve some data. So over the course of the history of browsers, there have been a large number of side channel attack scenarios and timing-based ones in particular. And as a result, modern browsers do implement some protections against certain timing attacks. Some of them still exist and are still dependent on application features and capabilities and the code bases, and we'll look at that in a bit. Many of the more recent mitigations exist to mitigate Spectre-like attacks that we won't go into depth about. There are lots of good videos out there detailing how speculative execution type attacks work, which are very interesting. I'd encourage everyone to take a look at those. We won't be covering them. And as I say, nevertheless, despite protections that do exist in modern browsers, there are attack vectors that still do exist in the right situations. To give a really solid example of what a timing-based side channel attack might look like, consider this pin-based locking mechanism, and let's say that it requires 4 digits, right? So you set a code with 4 digits, you hit the button, it's locked, you want to unlock it, you hit 4 digits again, and then you click the unlock button. So once you enter those 4 digits, it sends that data to whatever piece of code is going to determine whether the pin that you've sent matches the pin that has been saved that's been used to initiate the lock. And if we assume that the way that this mechanism works is it does a comparison digit by digit, and as soon as it encounters a first incorrect digit, incorrect being a non-match against the correct pin, as soon as it hits an incorrect pin, or digit, let's say it returns. And this makes sense, I think, from a computational point of view. It's a quick way to evaluate a pin because it returns as soon as it knows with the first digit that it's failed. But if we assume that there is a significant time difference, depending on how many digits are evaluated, this mechanism gives us an opportunity to more easily guess what the actual pin is just by observing the timing differences in the comparison algorithm between the pin that we submit and the pin that has been used to actually initiate the lock. So let's assume that the actual pin is something like 8473. And we can ignore the code snippet for now, but I'll come back to that after we talk through the example. If I guess 1111 and the algorithm compares the pins digit by digit, well, it compares the 1 to the 8. It sees that those are different, and the algorithm returns. So one comparison, it takes 1 second. If we guess again, 2111, we have the same result. 2 is not 8. It compares 1 digit, and then it returns. But if we guess the correct first digit, then it does that comparison. It says, okay, there's a match. And then it looks at the second digit, compares that digit, and sees that, well, 1 is not a 4. So that's a rejection case. So that takes now 2 seconds because we've done 2 comparison operations. And as a result, there's a significant timing leak. And the JavaScript on the right-hand side is essentially just a codified version of this algorithm. We're running through a loop, and that is comparing digit by digit our pin. Now, the timing differences in this case, I mean, I could have implemented some type of sleep into this to make it align with 1 second. The timing differences of this code will not be on the order of 1 second on any modern hardware or anything approaching modern hardware. But if you have enough of if you have a capability to measure very precise differences in timings, this is still an algorithm that is not timing safe. There is still potentially leaked information because we're breaking out early. So because of this mechanism, because of how it works, digits can be guessed sequentially using time as a side channel for correctness. So without this mechanism, if you think of a guessing attack, you're guessing space is essentially 10 to the power 4, which is going to be 10,000, right? There are 10,000 roughly unique numbers for that 4-digit code that you're going to be able to enter. And so the maximum number of time it could possibly take you to guess it, assuming that you're guessing the correct one last, or the maximum number of attempts is going to be 10,000. But if we make use of the timing channel and we use time to determine when we've hit a correct digit, then instead the maximum number of guesses is actually reduced to a guessing space of 40. So from a guessing perspective, it makes it a lot more practical for us to be able to conduct a guessing attack to determine this pin. In practice, nothing is ever quite this neat, and there are many factors that can impact being able to determine timing differences. Of course, one of the big ones, especially when we're dealing with network communication, is noise, jitter, everything that could cause there to be a difference in how long it takes us to receive a response that isn't related to the underlying completion or computation of the algorithm in question that is vulnerable to the specific type of timing leak. And so when we're looking at these in practice, often we want to employ strategies to reduce noise, make our timing attacks really tight, and in some cases we even need to conduct statistical analysis, which in this very simple scenario that I presented, we don't need to do any, if we assume that the timing differences are very consistent and there's no noise, statistics don't need to come into play. But if you run into a situation where the noise is such that there's variation under the same state and conditions, you might need to conduct statistical analysis, which maybe I'll do a future session on, but we're not going to dive deep into that today. And now we can look at a practical example within the browser. So in this situation here, let's assume that we have an application that has a vulnerable method. And that vulnerable method is a search function that lets us, within the URL, enter a queue parameter in the query string that is our query in order to engage the search function of this application. So the application is called Health Portal. So we assume that this is some type of portal that provides, that has some sort of information on its authenticated users relating to the status of their health. And the search function lets them search across that, right? Maybe they're searching for medical history, maybe they're searching for a pharmaceutical record, whatever, right? It doesn't particularly matter. The way it works, though, is users search, and if there are results corresponding to them that are specific to them, those search results will populate the page. Now, the assumption that we're making here is that there's going to be a difference in timing depending on whether search results actually populate the page or not. And so the way that this exploit works here is that this code is from the perspective of a malicious site. So we're on a malicious site, and we're assuming that we can send cross-origin requests that remain authenticated. So if we're talking about HTTP cookies as a mechanism for the user to make authorized requests, we're assuming, of course, that all of the mechanisms that would prevent those cookies from being included, like a strict same-site directive, we are assuming those are not in place, of course. So ignoring modern protections for a moment, which, of course, is still relevant today across the web with the absence of that attribute used on cookies, and also oftentimes it being sent or set to none. And what we're trying to do is we're trying to conduct a search by sending on behalf of that user a cross-origin search, including specific keywords. And then using those keywords, we will determine whether there was a corresponding search result that matches that keyword. So in the example here, we're searching diabetes, right? The attack here is us trying to learn something about our victim who has navigated to our malicious site. And if we search diabetes and there is a long period of time before the response returns, yes, we cannot read that response because of the restrictions of same origin policy, but we might be able to deduce that response contained results because of the amount of time that it took to return. And because of that, because we controlled the nature of the search, we injected our own parameter, the word diabetes in this case, we can infer from this that the patient has some medical history related to diabetes or diabetes medication, and therefore we have learned something about our user who otherwise is anonymous to us. And so these attacks can, when they work, be quite devastating in leaking individuals' information. a lot of the mitigations for these attacks we've kind of looked at throughout this series already. But the first one that we haven't is eliminating the source of the side channel. So if we're thinking about that search function, one of the ways that you can implement a mitigation to prevent leaks is just make sure that the responses to searches always take the same amount of time to generate regardless of the content that's going to be returned. This can actually be a little bit harder to implement than it first seems, and I think it's probably one of the reasons why this exists a lot of the time, but there are a lot of practices that do exist that can help developers make timing safe algorithms, but this is probably the mitigation that I think makes the most sense, is just remove the leakage of the information. That said, we can also use a lot of the mitigations that we have looked at throughout the series, like validation of the fetch metadata, restricting cookies with the same site attribute, implementing a cross-origin resource policy, using CSRF like tokens, which I guess we haven't talked about CSRF yet, but we will inevitably. All of these mechanisms are ultimately designed to prevent a malicious application from sending a request to ours and having it processed to actually accomplish the search. Those protections can work too. It may not work if you have an application that needs to support those types of cross-app, like cross-site, cross-origin type requests. So therefore, I do think in most cases it makes sense to eliminate the source of the timing leak. Browsers also do implement, as mentioned, some of their own protections that reduce timing resolution. So using Performance Now as an example, it is clamped by browsers. You can't use it to make highly precise timing determinations. And I think all modern browsers actually add a little bit of jitter to it. So they add their own noise even when you're just trying to read time in JavaScript. Now, I don't think that the clamping and the jitter is very significant to prevent attacks against applications that a lot of modern applications based on the performance that I've seen across apps that exist on the web. But nevertheless, those mitigations may prevent a lot of attacks, especially ones that require a high precision of timing. Notably, some of this is relaxed when site isolation is achieved, which is a state that came up in a previous session. Moving past timing-based side channel attacks, going to introduce compression-based side channel attacks, which are very interesting types of attacks which typically exist in the context of an attacker being able to observe encrypted traffic. And before we talk about these types of attacks, it's worth talking about how lossless text compression works, or at least how it can work. And we're going to use as an example a substitution code, commonly known as a dictionary method, and we're going to look at that through an example. So let's say we have the phrase, rain, rain, go away, come again another day. And we have, and I didn't come up with that phrase. That appears to be a common phrase used for examples like these, by the way. If we have step one, identification of the repetition. So these steps are employed by the compression algorithm. So first, it identifies repetition. It sees rain, and it also sees subset of words like AY is repeated. Now, this window that a compression algorithm potentially looks in for repetition, the way that that is implemented, the size of it can vary quite substantially depending on the compression algorithm and configuration. But we're going to ignore that for now, and we're just going to say it found rain duplicated, it found AY duplicated, and its next step, once it finds duplications, is to create a dictionary of those duplications. So it creates a dictionary. It says 1 is going to correspond to the word rain, 2 is going to correspond to the letters AY, and then in order to create a compressed version, we save our dictionary. That's going to be at the start of our compressed text, but then we replace all of those dictionary items in the actual original plain text with the references to the items in the dictionary. So instead of repeating the word rain twice, it now has those placeholders up from the dictionary, 1 and then 1, which ultimately reduces the size of that text. Now, I note that this is a very bad example because I think the combination of this compressed text plus the actual dictionary. Because remember, if you don't have the dictionary, you don't know what those underlying words are that are being referenced. So when you actually compress text, you have to include both for someone to be able to decompress it. But in this specific example, if you were to combine the dictionary size with the original text, I think it might be larger or about the same size as our string. So not a great compression example, but nevertheless, it illustrates the mechanism. And it turns out that this mechanism can be abused. And one of the more popular ways in which this can be abused is the breach vulnerability, which was reported as far back as 2013, if I remember correctly. Breach stands for Browser Reconnaissance and Exfiltration via Adaptive Compression of Hypertext, which you can clearly tell they're really reaching to make the word breach out of this, which is a very common theme in cybersecurity for whatever reason. I guess it makes it a bit more catchy, so it's easy to catch on and and remember, certainly. In the case of breach, when you search breach in the context of cybersecurity, though, you also get a lot of things that are not related to this specific vulnerability. Nevertheless, let's talk about the requirements for this. So breach is a vulnerability that can impact web applications that are using compression and are using encryption. And so these are the requirements of the attack. The attacker must be able to inject chosen plaintext into a victim's request. So it's another situation where we have some probably cross-app issue, right? We have an attacker who has a malicious application, and we have a target application, and we have a victim user. And the victim user is navigated to the attacker's malicious site, and that malicious site is creating requests and sending those to the target application on behalf of the user. So another situation where we're considering the worst possible cross-app situation where the user's authenticated cookies are being automatically sent by the browser. The next condition in order to be able to conduct this attack, or the next requirement, is that the attacker must be able to measure the size of encrypted traffic. One way to do that that's quite simple is the attacker sits on the same network. So the attacker is on the network of the user. They can sniff the traffic. If it's encrypted, they can't read the data. But if they can see the encrypted data, they can see the size of the packets, even though they're encrypted. And the final requirement is that the outcome of these requests that are being sent is that they contain sensitive information, and crucially, that the plain text that the attacker chooses to send is also incorporated into those responses and compressed in those same responses. So in order to be able to conduct these attacks, I guess I've already covered this looking at the technical approach. So the attacker causes a victim to navigate to attacker-controlled site. They can inject malicious cross-origin communication to target an app. The attacker sits on the same network as the victim and can intercept encrypted TLS communication. Not even necessarily intercept, just sniff it, just see it, just observe it. And point 3, HTTP compression is supported by the app and used for that response, incorporating the plaintext included by the attacker. So just as a quick aside, talking about HTTP compression, HTTP natively supports compression, commonly gzip or Brotli. The browser typically requests compression, and the server conforms to that. So in the images here, you can see an HTTP request where we have accept encoding with gzip and Brotli BR. And then in the response, the server has determined that it is going to use Brotli, and it includes the response as binary looking like compressed data. So data that is clearly not intended to be human readable. And you don't see this a lot if you're doing web application penetration testing, because tools like Burp automatically decompress these for you. So it's not immediately obvious when HTTP compression is and is not being used unless you toggle the settings to actually observe it. So let's walk through how the attack actually happens here. So consider a target web application that behaves as follows. There's HTTP compression supported, of course, which is one of our preconditions. And this applies just to the HTTP bodies, right? So the response body that's returned from the application, that is compressed. In our target application, we have an endpoint. This endpoint I'm just calling get data. It's on target-site. And let's say that in the worst case scenario, the response includes the user's password. Really bad thing to do. Generally, the application shouldn't even have access to plain text passwords, though they're out there. I've seen them. So we're going to say that this is the state of our vulnerable application. It's returning a password in the response, which normally the attacker wouldn't be able to read, making cross-origin requests because of same origin policy. But let's say that the same endpoint also accepts data in the form of a parameter, which I've called reflect me, and it takes that data and it incorporates it into the same response that includes the user's password. And finally, of course, we're making the assumption that the app is using HTTP cookies with same site none, or some other mechanism allows us to make authenticated requests on behalf of the user. And just as another aside, of course, at Digital Boundary Group, we do have a finding for breach attack potential. I will make another aside to this aside. Realistically, I've never heard of the breach attack actually being exploited in the wild. It requires a large number of preconditions, practically speaking, and oftentimes there are many more vulnerabilities that are much more easy to exploit against applications. Nevertheless, breach is, I think, a really great example to explore how different complexities and elements of web applications can lead to very interesting vulnerabilities. So we will continue forward. CyberChef made a very good test bed just to compose some, just to look at how the compression would potentially impact the size of responses. So that's what I'm using here. So let's say we have a request that includes reflect me, the parameter, and remember the attacker is initiating this from their site, and the user, they're unwittingly sending it to the trusted target application. And so let's say that this reflect me parameter, which is controlled by the attacker, contains their guess. They're trying to guess a password. And you might think that, well, if they're guessing a password, they might as well just do that against the login mechanism. And you'll see momentarily why this can actually be more efficient to guess a user's password or whatever other secret is returned in these responses. So in this baseline attempt, we have some guess. And if you look at the HTML that's been constructed here, the response contains the user's password, and it just says your password, my super secret password 12. You can also see that we have the reflected value from the attacker. They have guessed some guess. Now remember, the attacker can't read this. All they see is the encrypted traffic, and so the only thing that they can really deduce from this is based on the size. So I've also included the response size here. It's cropped out of the CyberChef image, but CyberChef does display the size of the compressed text, but I've just included it here for simplicity. So in this case, it's the size is, we'll say 236 bytes. And now, remembering what our password is, my super secret password 12, we'll look at a few different guess attacks by the attacker. So they try some guess, okay, 236. And then they try guessing 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And they get 239 bytes. Okay. They try guessing my. They get 230 bytes. And then they try guessing my guess, and they get 233 bytes. Now, that's kind of an interesting result because adding guess as 5 bytes is larger than 3 bytes. But it's not it's not that interesting yet. And it doesn't match our password. But these are kind of the thought processes of what you would be thinking when conducting this attack. And so then the really important one, look at the next one, my super, that's now 230 bytes. So we're now guessing the same length as my guess above, but, and we know that our data is reflected, so we would expect that the response size would be about the same. It's actually shorter in this case. And the reason it's shorter is because the compression algorithm is recognizing that the password returned, which contains my super, contains that same, that substring matches the other string that our attacker submits, my super. And so it's making that a part of its dictionary. And that allows it to compress the response further so that it's shorter. So that's how we, as an attacker, know that we've actually hit a true match here, is that we've guessed the same length of input. Our size that we're seeing as we see these packets go over the wire are shorter. And if we then try my super secret, we've injected a whole word here, secret, and the byte difference there is, it only goes up by 1 in this case. And there might be varying factors, especially application-specific ones, that either introduce noise or might cause deviations. But generally, under ideal circumstances, you can actually use this technique to identify when you're injecting something that matches another string that exists by looking at the compressed size not increasing as much as you would expect it based on the string that you're injecting into that response. And so ultimately, you're able to continue along this path. And this is why it's very different than injecting or doing just straight up password guessing, right? If you're doing straight up password guessing, you are going to be it's not going to give you hints in most cases. I mean, you would hope that the application is not going to give you hints, but in this case, it's effectively giving you hints as to what the password contains. So this is why this approach is more effective than password guessing. I mean, in most cases, you probably aren't going to be able to guess a password with a breach vulnerability, but it lets you much more quickly identify by matching subsets of the target string what the actual secret is. If you look to a lot of examples of the breach vulnerability that's been written up, a lot of them focus on CSRF tokens as an example, which are viable targets, assuming that your CRF token is not being regenerated on every response. But I think a more practical target, assuming that you're actually in a situation to be able to conduct a breach attack, is going to be some other secret that is much more easy to guess. And probably if you're inspecting traffic, you're looking at Wireshark, so you're ultimately looking at the size of the encrypted data. So how do we mitigate breach attacks? Well, we can disable HTTP compression, and that's a perfect mitigation. If there's no compression, you really can't do this attack. That said, compression can be quite significant in reducing the amount of network traffic that is being sent. So for performance reasons, it may make sense to maintain compression. So there are other mitigations as well. Random padding can be introduced to obscure the length. Cross-app protections can be implemented, like all the ones we've talked about. Just, for example, restricting when cookies are going to be sent using same site. The application could also be re-architected to remove potentially vulnerable functionality. In the example that we looked at, obviously the application should not be returning the user's password. If the secrets that are being returned don't really need to be viewed in that context in full, they can be masked, ideally removed. And a couple of other potential mitigations. Enforcing TLS 1.3, it actually adds packet padding, which may obscure traffic analysis, and HTTP version 2 as well. In some situations, multiplexing may further obscure traffic. I wouldn't necessarily rely on this, though, and I personally haven't experimented with the impact of HTTP2 multiplexing on breach vulnerabilities. It's worth mentioning that breach is not the first popular compression type side channel attack. It's followed KRIME, which was published the year prior, 2012. And this one is kind of less interesting because it's, I think, definitely not possible on the modern web. KRIME stands for Compression Ratio Info Leak Made Easy. So again, it's another stretch to get a really precise acronym for your vulnerability. Now, it's basically identical to breach in terms of how it works. However, it relied on TLS compression rather than HTTP layer compression. So with HTTP compression, it is dealing with the HTTP bodies. With TLS compression, it includes everything that's included in that TLS connection. So that means it also included headers, and therefore it would have included headers like cookie headers. And so the scope of applications and situations where this vulnerability could have been exploited were much wider than for the breach vulnerability. However, TLS compress then encrypt, I think, is pretty much no longer utilized across the web. So I do not think that KRIME remains a viable vulnerability. Maybe there's some obscure exceptions to that with old technology, but probably quite unlikely to actually be exploitable anywhere. It's worth noting that when looking at side channel vulnerabilities and mitigating them, as we've already seen, there are often conflicts between performance and security. And the screenshot I'm including here is the same screenshot of the code we looked at with the lock example, where we are returning as soon as we find a digit match. And so we can implement a secure alternative to this, but one way of doing that requires going through the full comparison rather than aborting early so that we can achieve a constant time in the amount of computation. And that would be a timing safe implementation, but we're also losing a little bit of performance. And you'll see these types of trade-offs come into play a lot with side channel attacks. And I think that's why we see a lot of side channel attacks arise from security researchers looking at performance features, right? HTTP compression is a performance feature. If we're talking about the Spectre vulnerability and similar vulnerabilities using speculative execution, that's a performance feature of CPUs that's being abused. I thought it'd be worth mentioning one very fun finding from my early days as a application security tester. And this is one that I've always wanted to write up, and I just haven't yet, so I'll share it here in this presentation, in the slide. And that is what I've called the PDF compression side channel oracle. As far as I've seen, this has not been written about elsewhere. It's basically the same as breach, but uses PDF generation, which is a pattern that I've seen a few times that incorporates user supply data. And I've seen it used in exactly the way that it could be exploitable if you had the same context as an attacker would for a breach attack. And this is because PDF generators will often use lossless text compression. I haven't explored the full range of what is used by all PDF generators and the specification of PDFs, but I have encountered this in at least one case where PDF generators incorporated user supply data from a URL, and the PDF included other sensitive data, and that data was compressed in a way that if you had that context of being able to send cross-app requests containing whatever URL parameters you want, and you could observe the encrypted communication, you would be able to guess the sensitive information that resulted in that PDF. Now, just like the breach attack, I think realistically, this is not likely to be exploited probably ever. Once you've achieved the preconditions for this, there are probably so many other things that you could do as an attacker. But nevertheless, I think it's another great example of the types of non-obvious side channel attacks that can arise through a combination of factors and behaviors on the modern web. And yes, there are more mitigations against these types of attacks with modern browsers, especially surrounding the protections of cookies. Nevertheless, there are still a lot of applications out there that remain vulnerable to these types of attacks. As far as testing goes, these can actually be very, very hard to discover. You need to understand both the present state of browser mechanisms and protections and APIs. You need to have a strong understanding of the application that you're testing, how it works, and you need to identify specific functionality and features that might actually be abusable. And I think that can be challenging too, to even conceive of what might be worth abusing or what you can possibly gain information from using these types of attacks. I think one thing that will help inspire these types of attacks will be when I cover in a future session cross-site leaks more broadly, which I think these attacks covered today all reasonably fall under that class. And in particular, we'll be looking at a lot of examples from the cross-site leaks wiki, which is a great resource. It includes a lot of modern mechanisms that can be abused, and I think we'll give you a good idea of the various attacks that people have conducted. And I'll probably also do a separate session on case studies, looking at cross-site leaks that have occurred from bug bounty programs that have been disclosed publicly, and anything else I can dig up that might help inspire different attacks. Now I usually close with OWASP ASVS requirements. In this particular case, I think all of the relevant requirements have been covered in previous sessions, just because we've already talked about a lot of the protection mechanisms that can be invoked by developers in order to prevent certain types of unwanted cross-site and cross-origin communications. So that's it for this session.